And for the keynote, it's my pleasure to announce a very prominent speaker, Philip Wong. He's the Willard and Ines Kerbel Professor at the School of Engineering at Stanford University. And before joining Stanford in 2004, he was with the IBM TJ Watson Research Center. Then from 2018 to 2020, Philip Wong took leave from Stanford University to become Vice President for Corporate Research at TSMC, the world's largest semiconductor foundry. Since 2020, he's back at Stanford, but he still remains in a chief scientist role at TSMC. And this means he will be able to really speak from a lot of very relevant experience. So we are very much looking forward to your talk.
Thank you. Really appreciate the invitation to speak in here. Thank you, Warner and Max Lemmy, for inviting me to come and give this talk. See a lot of good friends in here, which whom I have worked with over the years. Got Gutenbergs and Daniel Mini, and currently I'm working with Pabana Bohan, who he spoke about our current work yesterday in the afternoon. So today I'd like to talk about compute with memory. A lot of work, some of the papers you see today, on yesterday and tomorrow, relates to compute in memory or in memory computing. This title is not a typo. I really mean compute with memory, not compute in memory. So I'll explain why as we go forward. First of all, I'm sure that you understand today that the challenges of today's computing system is really seeing three things all simultaneously hitting us at the same time. First is the memory wall. For computing systems, there's a difficulty of getting enough memory at enough bandwidth to the compute element. And secondly, the industry has been going through a lot of miniaturization over the last 5 decades, and resulting in higher and higher device density and more devices on the same chip. But today, you're seeing physical limits of continued two-dimensional device scaling, and so we are hitting this, what we call miniaturization wall. Coupled with that, the third part is really, if you look at neural network model size, they are going through extremely fast, rapid expansion in the number of parameters required to execute the neural network. And so this neural network size explosion really compounded these two walls that I mentioned earlier for both the memory wall and the miniaturization wall. Okay, so what are we going to do about this? And that's very a key issue that we need to address. So let me first describe one slide about this memory wall problem. If you look at this chart in here, it shows two sets of data, processor peak throughput in gigaflops per second on the blue data points up at the top, and then on the down on the line below is the other green data points, the memory peak bandwidth in gigabytes per second. Over the x-axis is years, so this is the actual data from the GPU products. And you see that both are growing exponentially over time, which is wonderful. But they grow at a different rate. And the top line, the processor peak bandwidth, grows a lot faster than the memory peak bandwidth. So as a result, over time, by now, we have really opened up what we can recognize as a bandwidth deficit. Namely, the processor is way faster than the amount of data available to them coming in through the off-chip memory. So therefore, the processor is oftentimes, even though they are fast, they are lacking data to work on. On this second part of it, on miniaturization, if you look at the SRAM, the memory that is on the logic chip, the SRAM cell area, they are going down again on an exponential fashion. And however, in recent years, you see that the scaling trend for SRAM cell has really slowed down. If you look at the bottom line here, you are beginning to see that SRAM cells don't scale anymore. for a variety of reasons, from circuits, the signal noise margin, as well as power supply and other reasons that prevents them from physically scaling down further. So in other words, continued scaling down of SRAM cell sizes to give you more and more SRAM density on the logic chip is getting to be slower and slower to come by as we go forward. A third is, of course, you all know, for those who are working on neural networks and AI systems, that the number of model parameters explode super exponentially. So it really compounded the problem that I mentioned earlier, namely the bandwidth deficit, and also the fact that the available on-chip memory becomes really constrained due to the lack of further device scaling on SRAM. So the challenges, to summarize again, the challenges of today's computing systems are three things. A, the memory wall problem. Two, two-dimensional miniaturization has to really slow down. And three, the amount of memory required for executing the neural network has really exploded exponentially. So the next question really is, how do we get to the next 1,000 times of improvement in terms of energy efficiency versus today's best AI hardware? How do we execute this AI hardware much more energy efficient and also with less latency and so on? All right. If you think about the three problems that I articulated earlier, really there is a strong need for lots of memory available to the compute core, and the question then is, how do we get this lots of memory? Talk about memory. I work on device technology. There are many, many options. They all have very different device characteristics. You may have heard today and throughout this conference a lot of discussions about random access memory, resistive switching, RRAM, and ferroelectric transistors. And earlier you heard about phase change memory. So there are a lot of options. And from a device technology point of view, it is a wonderful opportunity here to offer a solution there. And also, all of these solutions provide a variety of different characteristics. But more importantly than the device characteristics and the fabrication technology is, how do we put them together to provide large capacity and high bandwidth? And the way to do that is really to combine and merge the computation and the memory and merge them together. Now, the way to do that is to put the memory and the logic on the same chip on a three-dimensional fashion. Why three-dimensional? Is because you want high bandwidth. You need a lot of pin accessing from processor core, accessing the memory simultaneously together. If you're limited by different two-dimensional chips on a separate chip, then the number of connections between the two chips is going to be necessarily limited, and also the density will be limited as well. So you need lots of computing logic and memory working together in a three-dimensional sense and connected vertically with ultra-dense vertical interconnections. And we've done some analysis of systems like this and convinced ourselves that really you can achieve from 100 to 1,000 times of energy delay product benefit if you are able to integrate all these things together. Now, that integrating chips together is integrating memory and logic together on the same chip allows you to have very dense vertical interconnections, as shown schematically on the y-axis in here. But that's not enough, because no matter how much memory you put onto the logic chip, there's still not enough memory. So you need to be able to access data and also compute off one single chip and put them into a system. So what you need to do is to put multiple chips together, and these monolithic 3D chips, which we call the next chip, the 3 stands for 3D, you should be able to put multiple of these chips together onto a system package. And on the system package here, the number of connections between the chips, necessarily the density is less than what is on the chip. However, then you will be able to see that you can achieve basically a continuum of vertical interconnection density, from very dense on-chip to less dense off the chip and connected through the package, either through an interposer or direct chip to wafer bonding with higher density. So the vision really is to have this what we call 3D mosaic of next chips. Each one of these next chip in here will be connected with each one of these next chip are monolithically integrated, but then there will be multiple of these chips that are stacked or assembled together onto a package to provide you a continuum of vertical interconnection density, either on chip or off chip. Okay, now the availability of a variety of memory characteristics provide a wonderful opportunity to really customize the memory, the choice of the memory technology to the application. The application requirement for the memory technology varies greatly. Some, as I listed in this several example applications, from data analytics to appending databases to machine learning accelerators and high-speed networking, depending on what you want to do. Some of the applications requires only write once and read once. Some of them may read many times, but they only append to the memory. And some of them require sparse random access, and you may be needing to read many times, but only write a few times, or reading many times and write many times. Or, for example, in high-speed networking, you mostly read once and write once, and the data will come and go. So data is more or less transient. So if you think about how we how we construct our memory hierarchy today, there is a little bit of mismatch. From a memory point of view, the primary bottleneck in system performance in scaling is the availability of a huge amount of memory in high density. From an application point of view, there's a huge variety of access patterns, but we only use a single simplifying abstraction that has cached byte-addressable read-write memory. So this is a mismatch coming from the fact that we have only 3 major memory technologies available to us today. We have SRAM, which is on chip, DRAM that is off chip, and NAND flash, which is basically long-term storage. And because we have only these 3 major memory that has very different characteristics in here, we need to manage through this cached hierarchy byte-addressable read-write scheme. So the answer to that really is to start from the application, looking at the diverse applications in mind, and see, okay, what are the read-write characteristics that we require, and then go forth and pick device technology that fits that particular application and build the entire system based out of that. But noting that going forward, there will be not only a dense on-chip interconnection in a vertical sense, but there will be inter-chip integration of the different kinds of chips on a continuum of interconnection density. All right, going back to the device technology, I'd like to show you some examples of how we can use different kinds of memory technologies for different kinds of applications. Let's start with RRAM. You hear a lot about RRAM in this conference in here. RRAM is a resistive switching random access memory, and it has high density, multi-bit capability with on-chip integration capabilities. So you can integrate the RRAM along with the logic chip on the same wafer. You can go very high density, and actually in some of the discussions yesterday with the participants, somebody asked me, can you build very high density? Yes, you could. You can build terabit class of RRAM by building 3-dimensionals, just like what you do with 3D NAND flash, by having a very simple process of depositing multiple layers, drilling a hole in one etch step, and therefore have a very low cost, high density type memory as a non-volatile memory, as I show schematically in here. There are indications that you can do this. For example, here, I showed this is a 8-layer, 2-bit per cell of RRAM, and you can build 8 layers with multiple bits. And also, you can have a rather high resistance value so that you don't need a selector to select one cell out of many cells in a big array. So that can be done, and also others in the community have done similar work that show that the 3D integration of RRAM is a possibility, at least on a device demonstration level. You can also do multi-bit resistor switching. It shows 4 conduction states in here with some distribution and and also cycling capability. And on the lower right in here, we try to program 128 resistance values onto the RAM, and it can be done. So in other words, you can do multi-bit. You can do almost like a grayscale data storage on the RAM itself. So with that, then you heard throughout this conference, you can do what we call computer memory. Because you can store all more or less like analog values or multi-bit values in this RAM. So you can do computer memory, and I'll show you some examples in here with our collaborators. You heard this morning from Gert Kohlenberg's this NeoRAM chip that we worked together on. And I'll show you another examples of the Sapiens chips, which I collaborated with another faculty, Priyanka Reiner at Stanford. So just quickly show you some key points about this chip in here. 256 by 256 RAM, compute in memory array on 130 nanometer CMOS. And again, we're collaboration with Gert Kohlenberg's. And we are able to show that you can reconfigure this chip because the RAM is programmable, and you can have high energy efficiency because all the memories are integrated on chip, on the logic chip, and you can have a very good inference accuracy compared to software. Here shows some of the energy delay product on the y-axis and the matrix vector multiplication at different bits position, and you can even comparing against a more advanced technology in here, 22 nanometer technology, you could get much better energy efficiency even at a more relaxed technology node. And here's another chip, collaboration with Professor Priyanka Reiner at Stanford. The Sapiens chips, basically a associated memory sitting in here in the middle, in the whole tool chain of feature extraction and embedding the feature vector in there, and then go forth and do the inference through the entire chain of events for embedding and retrieval. So it means that you can actually do a lot of these kinds of in-memory computing or associative memory, that kind of inferencing work through integration of RAM with the memory, with the logic itself. All right, so this is examples from RAM. And moving along to another type of device technology, ferroelectric FET. So those are devices, transistors, basically, with a ferroelectric layer in between the gate electrode and the channel here. And depending on the voltage of the top electrode, and you can flip the dipoles within the ferroelectric layer and change the threshold voltage of the transistors that are integrated together. It has very low power because when you're programming it, you don't have any direct current going from the programming terminal to the ground. So there's low power because it's basically operating at a capacitive weight of switching. It's non-volatile. You don't have a destructive read. You can do read many, many times without affecting the state of the memory cell itself. And you can use this ferroelectric FET in an innovative way by building multiple gates in here between the source and drain, which can emulate the behavior of a dendrite, which Kwabana Bohan talked about yesterday. And I'm not going to spend a lot of time on it because Kwabana already talked about this. But the key point is that you can build up multiple of these gates to emulate the functions of a dendrite, and therefore you can put these dendrites together in a dendrite-centric computing system. And so this is another way to really tightly integrate the logic, which is the computation by the dendrites, and the memory together onto the same platform. These are not separate chips of a FET and then a processing chip element, but rather really tightly integrated with the computation itself. Now, I mentioned there's a really strong need to provide as much memory that you can have on the logic chip itself. So one way to do that is to bring the off-chip memory today. It exists as an off-chip DRAM, dynamic random access memory, either on a traditional DDR type memory or a high bandwidth memory or HBM. Okay, so you can take these, in principle, you can pick this memory and put them together on the same chip. But then you end up with a really huge chip in here. So instead of a logic chip and an on-chip memory, which is a SRAM, and then you added all this memory in here, you ended up with a huge chip. Now, the huge chip, of course, will cost you a lot of money, so you don't want that. So what do we do? What we want to have is, instead of this huge chip, we want to have the logic chip, we want to have the on-chip memory, we want to have the traditional on-chip memory, the SRAM, but you also want another type of on-chip memory that is high density, doesn't take up a lot of space, and yet be able to have high speed because you're interacting with the logic very tightly onto the same chip. And you want to have low power, obviously, because we are all power limited and energy consumption limited in terms of our computing systems. And of course, when you're integrating the on-chip memory, a memory on-chip, you want to be, from a process technology point of view, you want to make sure that it is compatible with the logic itself. All right. And finally, if you are on-chip, most of the time, you are maybe writing to it a lot, and so you want infinite endurance in principle, right, as much as possible. And as you know, many of the non-volatile memory, because you need to write and read it, because they are non-volatile, they need to store the data for an extended period of time, then necessarily there is a trade-off between the number of endurance cycles that you have and how fast you can write, and so on and so forth. And so there is a intrinsic kind of tug of war between endurance cycle and retention time, and also the write speed, and so on. So the requirements for this on-chip memory are basically listed up here. You want high density, you want high speed, you want low power, you want compatible with logic, you want infinite endurance. All right. So what do we have? I think one of the things that we could have is this, what we call gate cell memory, which I'll describe a little bit further. It has fast read and write, high density, and it is more or less like SRAM-like. It's not SRAM, it's SRAM-like on-chip random access memory. All right, let me describe how it works. If you start from 1T1C DRAM, which is shown on the left-hand side in here, you have a write transistor in here with a word line and a bit line that supplies the data. You turn on the word line, and then you write the charge onto the storage node in here, denoted by SN. And the charge is stored into this explicit capacitor in here. That's why it's called 1T1C. That's why it's called 1T1C DRAM. One transistor, one capacitor DRAM. Now, what's the problem with that? Well, first of all, the 1T1C DRAM is very dense because it only consists of one transistor and one capacitor, as opposed to 6 transistors on a SRAM cell. Now, the problem with that is that you need an explicit capacitor. And this capacitor needs to be rather large because upon readout, you're sharing the charge on the storage node with the very long bit line that you have. And so because you're sharing the charge, then you need to have a very large amount of charge to start with. Otherwise, you won't have a lot of signal at the end of the day to sense. So that's a big problem. And because the capacitor needs to be rather large, then you need to, if you want to integrate it onto the chip, then it becomes very difficult unless you go 3-dimensional. And that's what people do in DRAM. You build 3-dimensional capacitors. And with these 3-dimensional capacitors, make it very difficult to integrate with the logic chip itself. So the solution there is to replace this capacitor here with the gate capacitance of a transistor here, shown in here. So you have a write transistor here. You turn on the write transistor, write the data into the storage node. And you use this transistor in here, which has a gain, to amplify the very small number of charge that you hear, and amplify them in terms of the current that you can read out. So that's why it's called a gain cell. It has gain in it, in the storage cell. So the gate capacitance doesn't need to be very large because you have gain now. And so in this case, you have shown it here on the upper left-hand corner, upper right-hand corner. The charge store creates an electric field, which then controls the current that goes through. And it has gain because of the transconductance of the transistors. Now, it does have this one small problem, which is you're storing a very small amount of charge, and this charge can easily leak away from this right transistor in here. As opposed to the DRAM, you're storing a larger amount of charge. You're not worried about leaking the charge away. So you need a different kind of transistor in here. You need a transistor here that has much lower leakage current. And that you can find that by choosing a different channel material, which has a high band gap, therefore it has very low offset leakage current. So just going back to the emphasize here, you are having one transistor here, storing the charge onto the gate of another transistor. Even though the charge store is very small, you can amplify it with the reed transistor in here. And you are not worried about leaking the charge away if you have a very low leakage current transistor, which I showed in here. And if you use oxide semiconductor as a channel material, you can have at least 3 to 4 orders of magnitude lower leakage current than the best silicon transistors that you can have. And as a result of that, you can store the data for almost like a few seconds. And a few seconds is very long compared to the cycle time of a processor. And so therefore, this is very suitable for data that is almost like transient data that goes through. In many of the neural network applications, many of the data processes are basically transient. Okay, so I told you that this is possible to have very long retention time. So here's a experimental measurement of this 2-transistor gain cell in here, writing the data into the storage node. You can see that the storage node voltage stays up high in 5,000 seconds, and from there you can infer that the offstate leakage current is about a few times 10 to the minus 18 amps per micron, which is at least 3 or 4 orders of magnitude lower than the best silicon transistors that you could find. Now, this is showing 2 of the transistor here, the green transistor, low leakage, low power, the green transistor in here, forming a gain cell. You can also use this transistor here, use a conventional silicon transistor, which is what I show in here, which I call hybrid gain cell. Hybrid is because you are integrating the silicon transistor with the oxide semiconductor in here. So schematically shown on the left-hand side, you have silicon transistor down on the bottom. You have a indium tin oxide, which is the oxide semiconductor transistor, integrated tightly together with this transistor here. So photographed in the middle. And the right-hand side shows the reed current coming from that reed transistor from this what I call a hybrid gain cell. And you have very high reed current at long retention time, as compared to the oxide gain cell. At a long retention time, you have a lower reed current. So the speed of the hybrid gain cell is going to be faster than the oxide gain cell. So to summarize, you can have 2 kinds of oxide semiconductor gain cell. You can have an oxide semiconductor gain cell in which both transistors are oxide semiconductors. And you can, because these are all fabricated and deposited at very low temperature, so you can basically stack multiple layers of these oxide gain cell on top of the silicon logic in here, achieving the high density that we want to achieve. On the other hand, if you're integrating a hybrid gain cell, you can take one of the transistors and make it a silicon transistor in here, and you can still put the oxide semiconductor on top of the silicon transistor. And because there are only 2 transistors, and one of the transistors is on top of another transistor, so the density of this hybrid gain cell is going to be at least 2 to 3 times higher density than the SRAM cell itself, which the SRAM requires 6 transistors instead of 2. The benefits of the hybrid gain cell is that it provides much better latency in read and access speed. So to summarize this gain cell, you can have infinite endurance because they are basically storing charge on a gate of a transistor, just like switching logic. You can have very high speed for the hybrid gain cell. Both of them are compatible with silicon logic. And because they only use 2 transistors and they can be stacked on top of each other, so you achieve high density. And it has low power consumption because you are leaking charge, very small amount of charge away. And on top of that, you have a lot of trade space in the design between retention time and bandwidth, power, energy, read-write speed, capacity, and the array sizes, how fine-grained you want the access to be, because you're only integrating on the logic chip itself. You're not limited to off-chip, in which you need to build very big arrays with very long bit line, very long word line. But here, you're integrating on the logic chip. The bit line and word line could be much shorter, and so you can have this trading between bandwidth and capacity and so on. And also, if you can integrate many of these layers together and to achieve a higher capacity, storage capacity. So going back to this title of my talk, compute with memory. And so we can do compute in memory, as I showed earlier, with the RAM and also with the ferroelectric FET, doing dendrocentric computing. But also, really, what you really want is a lot of memory on the chip. So you want to and even in the conventional storing ones and zeros type of computation, as I show you in the gain cell example, then you can have much better benefits in terms of having high bandwidth access to the memory. So broadening the concept here, in addition to compute in memory, we really need to think about compute with memory. You are adding thinking about how memory will interact with the computation in a whole computing systems. All right, so going back to what I showed you earlier, the way to get higher and higher energy efficiency and high performance in your computing system for all kinds of computation, including execution of the neural network, is to immerse computation and memory closely together, immerse them together, and closely coupling together, and having this memory and the logic on the same chip, multiple layers of logic addressing multiple layers of memory at the same time. And this is a situation which we call the next chip in here. And you need to be able to integrate multiples of this next chip in here into a package system, providing a continuum of vertical interconnection density. Today's chips are basically two-dimensional, and the interconnection density in the horizontal XY direction is very dense. But the vertical interconnection between the chips are not very dense, and there are several orders of magnitude different. But going forward, you should be able to integrate all these chips together, and therefore achieving a continuum of vertical interconnection density to really high density on the monolithic chip, to coarser and coarser, basically a hierarchy of vertical interconnection density between the memory and the logic together. So with that, I would like to say that opportunities going forward is extremely not only challenging, but also exciting, because we open up many, many opportunities. In the past, we have been used to kind of walking inside a tunnel. Everything is based on two-dimensional miniaturization. We know that by shrinking devices, we always get better energy efficiency, better device density, and so on and so forth. But going forward, we are almost at the exit of the tunnel. And so outside of the tunnel, you can go anywhere you want, and that's where the excitement is. With that, I'd like to thank our sponsors, the Industrial Affiliates Program at Stanford, with more than 35 member companies, Stanford Systemics Alliance, and our sponsors, the SLC JUMP Program, Chimes and Prism Centers, National Science Foundation, DARPA, and the Microelectronics Commons, as well as the Differentiated Access Memory, DAM project at Stanford, and also the Stanford Non-Volatile Memory Technology Research Initiative. And many of actually all the work I show you today are done by my students and postdocs in here, and they have been contributing to them. I would like to take this opportunity to introduce some of you to them. Sitting at the back, I think, is Harry Chen, my current student, working a lot on different integration of computing algorithm with the memory system itself. And Henry Chen is the one who is working on the dendrocentric computing with Kwabana Bohan. And two of my former students in here, Wei Wen, work on the NeRAM chip that you heard about this morning from Gert Kohlenbergs, and Haitong Li has been graduated, both of them graduated in the last 2 years, and Haitong Lee is work on the Sapiens chip that I showed you earlier. He's at Purdue University right now. Collaborators, Gert Koenbergs, Hua Chang-Wu, Bin Gao, and Priyanka Reiner has been our collaborators on the NeRAM chip. And Subhashis Mitra and I have been working on many aspects of this three-dimensional integration of memory and logic together. Kwabana Bohan you heard from yesterday, and Dr. Jian Chen is an adjunct professor at Stanford working with our students on the gain cell. And on the gain cell project, Shuhan Liu is a student who did all the experimental gain cell work that I showed you earlier today. And Kaustubh Jana worked on the modeling, and Jennifer Zhang works on the materials and device reliability and stability. With that, I'd like to thank you for the opportunity to speak in front of you. Happy to answer questions.
So thank you very much for this fascinating talk, and I see there are already people lining up for questions.
Thank you very much for your talk. I'm Zhong at Max Planck Institute. May I ask a question about Mosaic? So basically, stacking CPU, memory, and other computing parts together, would that bring the problem of overheat? Is heat dissipation a problem for this chip?
A very good question. You should listen to Kwabana Bohan's talk yesterday. He is working on ways to do different kinds of ways of do computing that allow you to scale up in 3D without overheating. Kwabana is sitting over there.
Hi, Shankar from IMEC. A great talk, and I wanted to ask about these semiconductors, IGZO, ITO, that you are using. So we are also working on that, and we face a lot of challenge on the stability of the device and everything. Like, do you have any comment on that? Like, how reliable will be our 2T transistors?
Yeah, so let me just go back to the slides in here. I'd like to introduce to you this concept of the hybrid gain cell in here. It is true, it is correct. In the current state of events, just like any device technology, there are many problems, and among them is the device stability. And basically on the oxide semiconductor, there are two kinds of instability. When you are biasing the gate on a positive voltage, you get positive bias stress, and then if you put it on a negative voltage on the gate, you have negative bias stress, okay? And if you look at the circuit in here, and the long time that you are standby or during read is a case where you store this one in here, and therefore you have a positive bias stress on the read transistor. If you use a silicon transistor as a read transistor, silicon transistors are very good, and it doesn't have a lot of the positive bias stress. Actually, Robin de Grief this morning has spent a lot of time on understanding the reliability of silicon transistors. And so if you use a hybrid gain cell, you get rid of this problem of having either positive bias stress stability or negative bias stress stability on the read transistor itself. Then you want to ask, what about the right transistor? The right transistor is basically you turn on the right transistor for a very short amount of time. And for the positive bias stress is very short because you only turn it on for tens of nanoseconds and you turn it off. And also between right cycles, the instability would relax. So therefore, the positive bias stress instability for the right transistors is way less than the case for the read transistor, and therefore the PBS, the positive bias stress problem for the right transistors is actually much less and also tolerable. And on the negative bias stress, and we have done some measurements which we'll show at the VSI symposium soon in 2 weeks, that the oxide semiconductor does not have a lot of negative bias stress instability. So for the time being, if you want to use the oxide semiconductor as is, the best way forward would be to do this hybrid gain cell. Now, if you want to do the oxide gain cell, then you really have to solve this positive bias instability for the transistor you put in here for the read transistor.
Thank you.
Thank you.
And we have a final question.
Hi,
My name is Chirag from Research Center ULISH. I have actually two questions. One is related to the next 3D chip which you showed. How do we ensure manufacturer reliability and yield in such a chip? And my second question is related to gain cells. Did you try, when we extend these gain cells to a larger memory size, do you think the retention time of 10 seconds or 5 seconds, what you showed, 5,000 seconds, what you showed here, will retain? Because I know in DRAMs, there are some cells which can keep the data for hours together, but when you see in a larger scale, because of 1 or 2 cells not performing, you need to refresh more often.
Very good, very good. Okay, on the first question about manufacturability and cost, there really is any fundamental reason why the manufacture and cost of 3D chips is not possible. If you read the Gordon Moore's paper on cramming more devices on the same chip, he actually literally wrote that there is no fundamental limit to having high yield. And so this is all practical, and also a matter of demand on the market. And so I don't think there's any fundamental reasons why it cannot be done. For example, it used to be said that chips cannot be too large because of yield. Now we have humongous chip. We actually have chips on a whole wafer, for example, in Cerebras. And so this yield problem and the cost of the fabrication is more a practical problem and also a market demand question rather than an application demand question rather than a fundamental engineering or physics problem. Okay. Second part about the, what is the second question?
It's related to the retention that...
okay, related to retention, yes. All these things right now, they're all at a university, right? So as you know, in the university, there's a lot of defects and extrinsic problems such as cleanliness and uniformity and things like that. So I don't have an answer for you right now because very few experiments have been done on integrating these materials in a large scale and look at uniformity and stability and so on. But then there are indications that why it can be done. For example, these materials are done by atomic layer deposition. So ALD is rather uniform and it's been used in the industry. All the gate dielectrics today are done by ALD in very thin layers. So from a fabrication point of view, I don't see there's a huge difference between this and what we do in, let's say, gate dielectrics in terms of uniformity and reproducibility and so on. And it is true that all memory are limited by the tail bits, right? And tail bits are important, and we won't know the answer to that unless we get to the point where we can build large arrays.
Thank you.
Yeah, so thank you very much again.
Thank you.
So let's thank thank the speaker.
Thank you.